Well, good morning. Hopefully you guys had a good weekend. I know I did. Today what I want to do is I want to talk about data, the way data is stored in digital systems, computers, devices that have microprocessors. And we know that the data is stored in the form of zeros and ones, but it turns out that data can be a number or a code. A number or code. Numbers have place values. Codes may or may not have place value. It could be that they have place value, or they could represent the data by the sequence of bits. So what I want to do today is talk about number systems, and then later in the week we'll talk about codes. So I want to start by talking about general number systems. General number systems. So we can talk about or represent a number system using this idea of a base and a power. So I can represent it like this. I can take the base to the power, and then that base, what that'll do is it'll tell you the number of symbols. So the base tells you the number of symbols in a particular number system. And if I take the base minus 1, that'll give you the value of the highest symbol. So what I mean by that is we as humans, we use a base 10 number system because we have 10 digits, 10 fingers, 10 toes. So if I represent the number system as a base 10 number system, then that base means that we have 10 symbols to represent the numbers in the number systems. And those symbols for a base 10 number system, we start with 0, and then we go 1, 2, 3, 4, 5, 6, like so. And if I take the base minus 1, if I take 10 minus 1, I get the value of the highest symbol in the number system. Now it turns out that this is kind of nice because this not only works for a base 10 number system, it works for any number system. And as you'll learn, if you don't already know, we're going to talk about several different number systems as we go through the material. Now let's talk about counting. So when I count with these symbols in a particular base, when I count, if I normally start counting with 0, but let's with 1. Remember, in digital systems we start counting with 0. So in a particular number system, if I start to count with these symbols, I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when I run out of symbols, what I do is I start here with 1 again, and I start to repeat this. So I go 1, 0, 1, 1, 1, 2, 1, 3, all the way up to 1, 9, all the way up to 19. Then I change this to a 2, and I still have to repeat these again. I go to 0, to 1, and so forth. Now, of course, this is kind of obvious, but what I want you to remember as we go through this, it works the same way in all number systems, not just base 10. Somewhere along the line, probably like 2nd grade, you guys learned about place value. So let's talk about place value. So for base 10, we'll just do 4 places. Maybe in the 2nd grade, they taught you that this was the ones place, tens, hundreds, thousands, and so forth. Now what we'll do here is we'll count these spaces. And remember what I said last week is when we count in digital systems, we always start to count with 0. So we're going to count these positions starting with 0. So we'll go 0, 1, 2, 3. So the 0 position is this first one. First, second, and 3. So these are the position count. And the reason you want to do that is if you start counting with 0, then what you can do is take the base to the power to get the weight of the number system. You can take the base to the power to get the weight of each place in the number system. So for example, I can write this as place as 10, the base to the power of the position. So this is 10 to the 0. This is 10 to the first. This is 10 to the second. And this one is 10 to the third. Well, as I said a second ago, this is kind of nice because it turns out this not only works with a base 10 number system, it works with any number system. So in general, I can do this. I can take a number system. The base will tell me the number of symbols in that number system. If I take the base minus 1, it'll give me the highest value of the symbol in the number system. And then once I know the base, I can get the weight, or what you would call the place value, by just taking the base to the 0 power, first, and so forth. So humans, we use a base 10 number system because we have 10 digits. It's kind of natural, we can count based on 10s. Digital systems, computers have basically 2 digits. They're based on switches, as you know, and a switch can be either on or off. So we need a system that represents 2 states, either one state or another, true or false, and that system is called a binary number system, base 2. So we'll apply the same kind of thinking to a base 2 number system. And if a base 2 number system, that means we have 2 symbols. If I take the base minus 1, 2 minus 1 gives me the value, the highest symbol in the binary number system, which as you already know is a 1. And so in binary, we deal with 0s and 1s. Well, what about place value? How does it work? In the binary number system, we can do exactly what we did here. In the binary number system, the place value would here, in base 10, this was 10 to the 0. On the binary number system, this would be 2 to the 0, 2 to the first, and so forth. And I can keep going if I want to. So what you can end up doing is this. Now remember, each digit in the binary system is called a bit. Bit is short for binary digit. And in this, now the bit positions, let's talk about that real quick. So the bit positions, when I have a list of bits like this one is called the least significant bit, and this one is called the most significant bit. This one has a heavier weight. And so I can write the place value in this box. 2 to the 0 is a 1, 2, 4, 8. And you can see the pattern here as I go to the left, each one of these will double. So I go 16, 32, 64, 128, and so forth. But what this box does, this is called 8421 code. 8421 code. And it will allow me to compare a base 10 number to a base 2 number, which turns out to be pretty handy. So let's say that I have the number 12. I think this is the one I use in the PowerPoint. So let's say I have a number 12. Now we're getting to the point where we're going to have several different number systems that we deal with. So now what we have to do is we have to specify what number system we're in when I write a number or when I do any kind of calculation with a number. So what I'm saying is, if this is a base 10 number, then what you want to do is subscript this with a small 10. You can see where you would run into a problem if I have this. If I have this, I have those two ones like that. If I leave it like that, I don't know if that's the number 11 or if that's the binary number 1, 1. I can't tell. But the way you will tell is by subscripting this. If you mean that that's the number 11, then what you're going to do is subscript that with a 10. If that's the number 1, 1, you'll subscript that with a 2, and then I'll know it's binary. So from here on out in the class, when you represent a number, you want to represent it that way, using that subscript. If I think about the number 12, 1, 2, and I want to know what does that look like to a machine, to a digital machine, then I can use this weight right here, this 8421 code. So I want to basically convert this to binary. What would this be in binary? Well, to get a 12, you start with the highest weight. I need one of these. I need an 8, and I need a 4. I don't need a 2. I don't need a 1. What that means is the number 12 in our number system to a computer looks like this: 1, 1, 0, 0, base 2. So you want to get used to doing that, converting from base 10 to base 2. When you type in a number on your keypad on your cell phone, when you dial a number and you hit the number 2, what's stored is not the 2. Let's say you type in a 12 and you're doing maybe you're doing some math on your cell phone. If you're doing math to number 12, when you hit the enter button, what goes into the machine is this, not the 1, 2, but a 1, 1, 0, 0, base 2. Every piece of information, every sound, every picture, anything that goes into a digital system is stored in zeros and ones, and it's stored as either numbers or codes. And so right now we're dealing with numbers. So one of the things you want to be able to do is to convert from a base 10 to base 2 or vice versa. Now in the slide, which I'm going to go over here in just a second, he uses a method called repeated division to convert a base 10 number to a base 2 number. Let me show you that real quick. And then what I want to do is go to the PowerPoint, because there's really more information in the PowerPoint. I just want to kind of go off to the side and show you some of the details on the board, because I think it's a little easier to follow if I do it right in front of you. And then we'll go through the PowerPoint and we'll pick up whatever I didn't talk about on the board. So in the PowerPoint, he starts with the number 47, base 10, and he wants to convert that to binary, and he uses something called repeated division. And what you do is you keep dividing out the number by 2, keep dividing the number by 2, and the remainder you get by dividing by 2, you'll if the number's even, there won't be a remainder, there'll be a remainder of 0. If the number's odd, there'll be a remainder of 1. Those remainders become the actual bits of the binary number. So it's a lot easier for me to show you than to explain. So for example, let's say I want to convert 47 to binary. 47, I'll leave the base 10 off, but you know it's base 10. What I'm going to do is I'm going to divide this by 2 and keep track of the remainders. Now remember what I said earlier, when you have a binary number, the leftmost bit is called your most significant bit, and the rightmost bit is called your least significant bit. This one has more value. Think about if I have $1,024, do you want to lose this end or do you want to lose that end? Well, you'd rather lose $4 than 1,000. So this is your most significant bit. Well, keep that in mind, because when you do this repeated division method, the very first remainder you get is your LSB, your least significant bit. So here's how this works. I'm going to divide that number by 2 and keep track of the remainder. So I go This is 2, and that's 3. So I get 23. 23 by 2 is 46. And I got a remainder of 1. So that remainder of 1 becomes one of the numbers and your binary number. But you got to remember that this is your least significant bit. That's your LSB. Now what I'm going to do is take this, and I'm going to keep dividing by 2 until I end up with my last binary digit. So I'm going to go 23. I'm going to divide that by 2. I get a 1 and a 1. 11 by 2 is 22. I get a 1. So my next digit is a 1. I'm going to take this number and keep doing that, keep dividing out by 2. So I got 11 divided by 2. That's a 5. 5 by 2 is a 10. I get a 1. So my next bit is a 1. So far I got now remember, this is my least significant bit. So I got a 1. That's this one, my LSB. I got a 1 and a 1. So I got a 1 and a 1. I got 3 1s. My LSB is this one. And so now I got a 5 here. So I'm going to go 5. Divide that by 2. That's a 2. 2 by 2 is 4. That gives me a 1. So I got a 1. I'm going to take this one. Divide by 2. 2 goes into 2 one time. Gives me a 2. So my next bit is a 0. And a lot of times what students will do is they'll stop right there because they get a 0, but you got to go one more time. You got to keep going. I'm going to take this 1 right here. Divide that by 2. 2 won't go into 1, so that's a 0. 0 times 2 is 0. And 1 minus 0 is a 1. So I get a remainder of 1. So that 1 right there is my most significant bit. So this is the divide by 2 method. So what you can do, guys, when I think in one of your homeworks, you got to show me you can do this. Just kind of go back and watch the video again and watch how to do this and practice that with some other numbers. So a 47 in our number system, base 10, to a computer looks like this. Divide by 2 method. So any questions over anything I've shown you so far? Any questions or comments? Because if not, I want to go to the PowerPoint, and that's kind of where everything is. I just wanted to, this stuff is easier for me to show you on the board than for me to just talk about it in the PowerPoint. I wanted to see where I get this stuff from. So anybody have any questions or comments before we go to the PowerPoint? Okay, but before I forget about it, I forgot who it was because the system didn't work in the last class, but somebody asked me about the software last, I think it was Wednesday, and I told you I would I'll send the link out if you want to look at the software, or when you buy the lab manual, which is coming up in a couple of weeks, when you buy the lab manual will either have a CD in the back of it. When I got mine, it had a CD in the back of it that had the software on it. If you buy a used lab manual and it doesn't have the software, or sometimes they'll give you a code that you can access and download the software with. If you don't have either one of those, there's a website you can go to and you can download. I think the software is like, I can't remember if it was 35 or 45 bucks. It's not that expensive. But somebody asked me about it on Wednesday, and I told you on Friday I would send you the link, and Friday the system messed up and we couldn't get on the class. So I'll send that link out today. I'll just put it on Canvas when I get to where I can log on there. And if you guys want to look at that software or download it early, you can do that. Anyway, let me go to the PowerPoint, and then I'll see if there's any questions. And if not, we'll call it a day. All right.
Quick question, I'm sorry.
Sure, go ahead.
Even I was talking to another student, and when we were searching for the book, like especially on Amazon, you get a lot of different covers. Like there's not one that is just readily available that you see come up multiple times. So is there any way that you could get us a picture of what the right one looks like?
Definitely. Actually, I have a picture. Yeah, I have one. I'll make it available. I think I already have it up on Canvas because somebody asked me the same thing last spring. I took a picture of it and put, so yeah, I'll make that available. That's a good idea. I got a picture of both sides of it, the cover and on the back, the ISBN number. So I'll make that available to you. Thank you for reminding me. That's a good idea. All right. So let's go through the PowerPoint. And some of this I've already talked about, but there's some other stuff in here I didn't talk about. So number systems and codes, and why do we want to study number systems and codes? We already know that data is stored in digital devices as either a number or a code. And so if we're working with the PLC, to really understand what the PLC is doing, we need to understand how that machine is storing the data or the information. So we got to look at number systems and we got to look at codes. I mentioned to you that we can represent any general number system with this notation where B is the base, or sometimes they use the term radix, and the power. And what's important here is what information does the base give you about a number system, and what information can you get by the equation base minus 1. Well, of course, we said that the base tells you the number of symbols in any number system, and the base minus 1 tells you the value of the highest symbol. Now you want to make sure you understand that, because I don't know if it's on, I don't know if it's the quiz, either a quiz or exam or somewhere, I ask you to make up your own number system, or I give you some weird number system like a base 4. And if you understand this, that no matter what number system you have, it's one of the ones that you're used to, like a base 10, is one of the ones that you're going to get used to, like a base 2, or base 8, or base 16. Those are the ones we'll talk about. You can make up any old number system, and the same rules apply. The base tells you the number of symbols in any number system, and the base minus 1 will give you the value of the highest symbol in that number system. And then if you take the base to the power of the position, b to the 0, b to the first, b to the second, for any old number system, it'll tell you the place value in that particular number system. So keep this in mind. So we gave the example here on the board, base 10, because this is the one that we as humans, we deal with base 10. And so we use the position here. I mentioned the position. We number the position starting with 0. And down here, I can use the base raised to that position number to get the place value or to get the weight of each position. When you guys talk about numbers and you learned about numbers, they call it place value. When you deal with digital systems, they call it the weight. The weight. It means the same thing. I don't really care how you refer to it, but you'll hear me use the term weight. And so, as I said, what's important when we deal with digital systems, since we have 10 fingers, 10 digits, we use a base 10. Think of a computer or digital device as only having 2 digits. If it's based on switches, a switch can be either on or off, so like it only has 2 fingers, so we need a base 2 number system when we deal with digital systems. So we use the binary number system, base 2. So we apply our equation. Base 2 means there's 2 symbols. The base minus 1 is the value of the highest symbol, which is a 1. And so in the binary number system, we're only allowed to use the number 0 or the number 1. If I need to count higher than the 1, then I start to repeat, just like I showed you how to repeat in the base 10 number system. It's exactly the same way. Here's how we actually represent. Now, you already know this because we talked about it. You know that if I want to represent a 0 or 1, we really do that by the presence or absence of a voltage. And for us in this class, a high voltage of 5 volts will represent a number 1. A 0 volts will represent a number 0 in binary. But what you see on your screen right now is an actual digital pulse. I think we talked about digital pulses a couple Fridays ago. And so you understand that if I want to store a 1, I would store 5 volts. If I want to store a 0, I would store 0 volts. If I want to move bits around, that's when digital pulses are important. I can move bits around by creating a digital pulse that's either high or low. But the point of this slide is that, as I said several times in the past, we know that we actually deal with the presence or absence of a voltage when we deal with digital systems. We just abstract from that as humans, and we represent the presence of a voltage as a binary 1 and the absence of a voltage as a 0. And it's probably the last time you'll hear me say that. We'll only deal with zeros and ones, but just remember, the machine, the cell phone, the microwave oven really only understands the presence or absence of voltage levels in certain places in the device. Now, here are some terms. If you guys have printed this PowerPoint out, like I recommend, go ahead and mark this slide because I'll ask about these terms. The first one, the bit, we've already used that term and defined it. A bit is a binary digit, so a bit is either a 0 or a 1. The term bit, I think most people are familiar with. But the next one, or the next two actually, there's this term called a register and a term called a word. I want to talk about registers and words. I'm going to talk about what they really are, and I'm going to talk about the way we use those terms in this class. A register is a device. You can go to, well, there used to be a place called Radio Shack. I don't think they're around anymore. But let's say you can actually go to an electronics store and buy a register of a certain size. A register is an electronic device used to store bits. So it's a physical piece of hardware used to store bits. A word is just a group of bits. So let's say I have a group of 4 bits. I can say that's a word. I have a group of 8 bits. I can say that's a word. I have a group of 16 bits. I can say that's a word. So I can make the number of bits and the word size be whatever I want for a particular machine. Let's say your cell phone or computer. The word size is defined by whoever designed and made the computer. So we say that word size is machine dependent. The point is this: a register is an actual piece of hardware. A word is virtual. It doesn't really exist. You can think of it as software. But for us in this class, we're going to assume a word and a register are the same thing. For us in this class, we're going to assume a word and register mean the same thing. So if you look at the third bullet point, registers are also called words. Well, strictly speaking, they're not. Strictly speaking, a register can hold or contain words, but a register is a piece of hardware. A word is a piece of software, or it's virtual, but we'll use them kind of interchangeably when we refer to words and registers in this class. So each word stores data as bits, and that's the place where when you store information in the digital device, you're storing those zeros and ones in registers. And so the size of the register becomes important because that determines the size or the amount of data that you can put into a particular machine. And the last bullet point, it says 8-bit and 16-bit words are most common. You'll find that word sizes, the number of bits in the word, depends on, well, I mentioned the fact that it's machine dependent. So if you design a computer, you can make your word size whatever you want within reason. But what's important is that word sizes are always a power of 2. So you can have a word size of 2, word size of 4, but you won't have a word size of like 15. Right? So word sizes are always some power of 2. And again, that's because of the binary number system that these machines are based on. So anything in blue on this slide, if you're marking this slide, there could be a candidate for a question on the quiz or exam. Make sure as you go through, I tend to do that. Any kind of vocabulary word or something I want you to remember, I'll highlight it in blue or red or something like that. So anything in blue here, bit, register, word, be able to talk about those on the quiz or an exam. Now, word size. So here's a 16-bit word, and I mentioned that before that the leftmost bit, this one, is called your most significant bit, and the rightmost bit is your least significant bit. But then you have this idea, at least when you have a 16-bit word, you have an upper byte and a lower byte. An upper byte and a lower byte. Well, what is a byte? A byte is 8 bits. By definition, a byte is 8 bits. So a byte is kind of thick. So a byte is always 8 bits, but a word is machine dependent. It depends on the manufacturer. So we have the upper byte and we have the lower byte. And then one thing you want to be able to do here is if you buy a digital device, specifically a PLC, how much information can that device store? How many? It turns out, now this is not true. This is one place where a regular PC and a PLC differ. The smallest piece of information you can access on, let's say, your cell phone or a computer or a laptop is a byte. Remember I said a byte is 8 bits. So everything, particularly letters, everything is based on 8 bits in the regular computer, regular PC. Well, PLCs are bit oriented. So I can actually refer to a single bit. And what's going to happen is, if you remember the actual diagram of the PLC that I showed you, or if you look at the video that I gave you the link to on Friday, where we talked about the input and output modules, and we mentioned the fact that on each module, the input or output module, you have those screw terminals that you can connect either buttons or switches or sensors to if it's an input module, or you can connect some kind of interface or maybe a small motor if it's an output module. You can connect wires to those screw terminals. Well, each one of those screw terminals is mapped directly to a position in memory. Each screw terminal, let's say you have a switch connected to a screw terminal and that switch is closed, then whatever screw terminal, whatever portion of memory that screw terminal is mapped to, if the switch is closed, that particular position will contain a binary 1. If the switch is open, that bit position will contain a 0. Now I'll say more about that later. Don't worry about that right now. That's actually a topic for like next week. But the point I'm making is, with regular PCs, regular digital devices, the smallest chunk of data you can access is a byte. With a PLC, the smallest piece of information you can access is a bit. PLCs are bit oriented. Other digital devices like PCs, cell phones, they're byte oriented. Byte oriented. So on this slide,
So,
you have a PLC.
excuse me?
Somebody have a question?
Yes.
Yeah, go ahead.
I still am confused of the difference between bit and byte. So a byte is a bit?
No, hold on a second. Let me see how to get out of this. Okay. So let me just put it all up here so you'll have it in your notes. So here are the terms that are important. A bit is a binary digit. So a bit is going to be a 0 or a 1. A byte equals 8 bits. So I got 1, 2, 3, 4, 5, 6, 7, 8. This is a byte. And then they have this thing, I don't know, it's on one of the slides. 1, 2, 3, 4. So half a byte is called a nibble. It's the actual word, a nibble. So a nibble is like 4 bytes, but I'm sorry, a nibble is 4 bits. But the one to know is this, that a bit is a single 0 or 1. a byte is 8 bits. So this is defined, this is written in stone, but a word is machine dependent. For us in here, a word, one word, is going to equal 16 bits. But there's a reason for that. When you buy a PLC, the number of screw terminals you have for the input module or output module determines the word size. So like on your simulation software, when you look at your simulation software, on the input module, you're going to see simulations of those screw terminals I keep referring to that you can connect the switches to. So this will be like screw terminal. You have these screw terminals on the module that you can connect wires or switches to. Now remember, we start counting with digital systems with 0. So this will be the 0th screw terminal. This will be the first one. Well, it's going to go all the way down. The last one is going to be 15. There's 0 through 15, which is 16 places for me to connect switches to. I can take a switch and connect the switch to that screw terminal. And I can take another switch or button and connect to that screw terminal. And what I was trying to explain a second ago is inside the memory of the PLC, I don't know if you watched the video that I sent you the link to on Friday. I referred to an output image table or input image table. Basically, it's just registers. All that was registers. So in the memory of the PLC, there are these registers. If I have 16 actual screw terminals on my input module, then I have in order for this to map to each screw terminal, I'll have a register that's 16 bits wide, so 16 bits wide. Now you got to remember, this register is in memory. It's not a real thing. It's a virtual structure, whereas this is actual hardware. But I can map this bit position, or this screw terminal to this bit position, and this screw terminal to this bit position. So when this switch right here is closed, there's a 1 in that register. When I open this switch, there's a 0 in that register. So it turns out that the software that you're going to use, the input modules have there's 16 terminals you can connect to. So for us in here, a word size is going to be 16 bits. If we had chosen software with 8 screw terminals, then the word for us would be 8 bits. But a byte is set in stone, right? A byte is always equal to 8 bits, and a bit is always a binary digit, a single 0 or 1. That make sense?
Yes, thank you.
Okay, that's a good question.
Because
Like
you said 1 byte is equal to 8 bit. I hear like an A, like 8 bit.
Oh no, 8.
Yeah. That's why I heard that the first time. That's why it wasn't clear.
Yeah, it's probably me. I slur my words sometimes.
It's okay.
So it's right here. 1 byte is equal to 8 bits. So look at the slide. When I look at the slide, it don't make sense. Look at the slide. Go back to that. Because what we're getting ready to do in that slide, we're getting ready to calculate. We're getting ready to calculate the size of memory in the PLC. So I think when I look at that slide, let me go back to it. It don't make sense when you look at that slide. So look at this right here. So it says we have it says if the memory size is 884 words, and a word is 16 bits, which a word for us is going to be 16 bits. If I have 884 words, and each word is 16 bits, how many individual pieces of data can I store? In other words, how many zeros and ones can I store? Well, that's just a simple multiplication problem. I got 884 words. Each word is 16 bits. So if I take 884 times 16, I can store up to 14,144 zeros or ones, or a combination of zeros and ones. And the same for this bottom example. This time they made a word size 8 bits. But the idea is the same. I still got 884 words, but this time each word contains only 8 bits, and so I can only store, I can say only, but this is a lot. I can only store 7,072 pieces of data, or 70, 72 zeros and ones. Okay, so this is all just terminology. Oh, so guys, on this slide, the one I just showed you, I'm going to ask, again, I don't know where, but somewhere I asked you to calculate the memory size like that. I think it might be on the exam, the first exam. I don't remember where it is, but you definitely want to, let me go back to that. This slide right here, if you remember I told you to print out your PowerPoints and as note pages so you can write on the side of them. So if you print those out, you can just I'll go through and I'll tell you, hey, this is on the exam. You can mark it. And then when you go back and you review for the exam, you know what exactly to look at. There's going to be a lot of stuff, a lot of papers and stuff for you to remember. So if you just mark stuff as you go along, it'll make it a lot easier for you to study for the exam. All right, so mark this slide and know how to calculate how many individual pieces of data you can store in memory of a PLC. And this is an example how you would do that. Oh, okay, now I need to, let me show you something real quick. Let me get off of this. It gets a little confusing. Now, hopefully it's not, because this is just terminology. But so somebody asked a question about, all right, a byte is how many bits? So 1 byte is 8 bits. Well, you also got this, it comes up in digital systems. You also got this thing. You got this KB like this, or it can be KB like that. It gets a little confusing. If I have a K and a capital B, and what this is kilobytes. If I have a K and a lowercase b, and what this is kilobits. So you want to know the difference between kilobytes and kilobits. Here's where it gets confusing though. Now you guys are engineers or I think you're all METs or MEs, and you know kilo is 1,000. Well, if I'm referring to this one, you probably better write yourself a note. So when you look back at this for the exam, you'll remember this. If I have a lowercase b, kilobit, then this kilo right here is 1,000, like you think it is. Kilo means 1,000. Kilo is 10 to the third. But if I have that K in front of a capital B, kilobytes, then this does not mean 1,000. It means 1,024. Because this has to do with base 2. So I don't know how you would write it, but you don't really see kilobits often anymore. You guys are probably way too young to remember, but back in the probably like the 90s, if you wanted to connect to get on the internet, they had something called a modem, and a modem was like literally it was a thing you could take the cradle of your phone, your landline, and set it in this cradle, and you actually had to dial up. You had something America Online. You had to have a dial-up service, and you had to connect. It was a nightmare. But those modems worked. They sent data. Remember we talked about the first week of class on that Friday? We talked about data transfer. There could be, you can have a register, and we can move information in a serial fashion and out in a serial fashion. So that would be serial in, serial out. I can move the bits in serially and move them out in parallel. So I can have serial in, parallel out. Well, it turns out back in the day, in the beginning of the internet, when people started to connect in the 90s, those modems actually sent information in serial out through the internet, through the wires, through the phone line. It was a really, really slow way of moving web pages. So the way they rated the speed of those modems, a modem is a modulator, demodulator. But the way they rated the speed of those modems was this way. Since they sent bits in single file, serial fashion, was kilobits. Well, now we don't use modems anymore. This is like old stuff right here. So now we think about kilobytes. So, but know the difference between K with a uppercase B, kilobyte, K with a lowercase b, kilobit. That's the easy part. The part you might forget is, because we engineers, we know that kilo means 1,000. Well, to a computer, kilobyte is 1024. So if I'm doing a calculation with this kilobits, I'm going to multiply by 1,000. I'm doing some calculation with this one, kilobytes, I'm going to multiply by 1024. Because to a computer, a kilo is not 1,000. To a computer, a kilo is 1024. Just write that down somewhere and remember it. Anyway, let me go back. That's kind of off topic, but not really. All right. Let me go back to the PowerPoint and find out where we were because I'm running out of time. I need to get through this. Okay, we were here. And so I went here and I was talking about, this is just kind of a note. Typically PLCs don't need a whole lot of memory like PCs and phones because, as I said earlier, they're bit oriented, not byte oriented. So we represent the state of a switch being open or closed with just a single place in the register. And in that register would be a 0 or 1. Whereas if I have a phone or a PC, if I want to represent the letter A or a pixel on a picture or video, that one pixel or that one letter is going to take 8 bits to represent in the memory of a computer or a cell phone. So it takes a lot less spaces in the PLC than it does in a regular PC. And so typically, you know, a memory size of 128, now this is kilobytes, not bits, because I have that capital B. So 128 kilobytes or 1 or 2 kilobyte is plenty of size for a PLC. A medium or small size PLC would do just fine with that amount of memory. Well, here's an example. If I wanted to know how many individual bits, if I have 2 kilobytes, how many individual bits is that? So I got 2 kilo is 1024, so I got to multiply by the 1024. 2 times the 1024, right? So that would be the number of bytes. If I want to know the number of bits, remember a bit, there's 8 bits in the byte, so I have to multiply by 1024 and then multiply by the number 8. Now, if you're confused by that, just go back and re-listen to this video and just kind of write the numbers down. It'll make sense to you, or you can ask me about it later. So I'm running out of time, so I'm going to kind of speed up. I've already done this example on the board. I started the class talking about this example. The point of this is that once you got these positions down here, the weight of each position, then it's easy to take a small, say, decimal number like the number 12 and figure out what would that look like inside of a digital device. You always start with the biggest weight first. In the 12, I got an 8, so I need one of those. I got an 8. I got a 4, so I need one of those. And then when I add this up, 8 and 4, I get 12. So I put the 2 zeros in positions in this over the 2 and the 1, and I get a 1, 1, 0, 0 base 2. A 1, 2 in our number system, a 12 base 10 is a 1, 1, 0, 0 base 2 in the binary number system. Is the way you think about that. And then I also showed this example. This is the example I showed the repeated division. I used the same number here, 47, and we went through and we kept dividing by 2. So what I would do there is go through and, I mean, if this is on a quiz, you got everything right there. You can look at your notes and all of that, but the quizzes are only 10 minutes, so you don't have enough time to search for stuff. You got to know how to do it and get through the quiz in the amount of time. But you know, what I would do is take another problem or something and convert it over. And I'll show you next time. You actually, if you have a PC or a laptop, there's a calculator. You can bring that calculator up and you can see all these different number systems in the calculator that we're going to talk about in this class. But I'll show you that if I think about it next time. So go over this, practice doing this. I think maybe the homework has you do this. Now, here's a important topic. If everything in the computer is a 0 or 1, how do you represent negative numbers? You see what I'm saying? If there's no way to represent this positive sign right here, I got the plus sign and I got a minus sign. because how do you represent the plus sign or minus sign in memory if the only thing in memory is a 0 or 1? How do you represent negative numbers? So I'm going to show you 2 different ways. Actually, there's 3 different ways to represent negative numbers in a digital system. And here they are. We can use something called a sign bit. A sign bit. You can use something called the ones complement, and you can use something called the twos complement. All 3 of these are ways to represent negative numbers in a machine. Now, typically, if you have a machine, you don't use a combination of these. You use a machine, you will have, if you're going to use a sign bit, then you will use a sign bit all the time in a particular design of a machine. If you're going to use a ones complement, you'll use that everywhere and all the time in the machine. Typically, the twos complement is what's used, the twos complement. So I want you to know what a sign bit is and how to use it. I want you to know how to get the ones complement, but we're going to focus on the twos complement in this class. So let's talk about a sign bit. A sign bit. The way a sign bit works is you have a binary number, and the leftmost bit, if the leftmost bit is a 0, then that represents a positive magnitude. If the leftmost bit is a 1, that represents a negative magnitude. Now, it's important that you look and understand that if I'm using the sign bit, then earlier we said that the leftmost bit in the binary number is called the most significant bit, the MSB, right? Remember we said that? The leftmost bit is called the MSB. Well, if I'm using the sign bit, then that's not true. If I'm using the sign bit, the leftmost bit would be the sign of the number, and the most significant bit would be the one next to it. So, for example, if you're looking at the slide right now, since we know this is a sign, these are signed numbers, I'm using the sign bit. This 0 right here is not the most significant bit. It's not the MSB. The MSB is this. So the magnitude of the number we're actually talking about, I'm putting the block around it right now. That's the actual binary number. What's out in front here is the sign of that binary number. So a 1, 0, 1 base 2 is a 5, and because I have a 0 out in front of it, it's a positive 5. The most significant bit is that 1, the leftmost 1 here. If I go down to the bottom, same thing, right? I got, let's do the negative 2. So here's the magnitude. This represents the actual binary number. So here, the most significant bit is a 0. The number out front, the sign bit, if I have a 1, then it represents a negative number. So that represents, in decimal, a negative 2. So one way to represent negative numbers in a digital system or digital machine is to use a sign bit. But you got to know you're using the sign bit. If you just walked in the room and I had on the board a number, I had the number 1001. You don't know if that's the decimal number equivalent for number 9 or if that's a negative 1. I got to tell you, hey, we're using the sign bit. If we're using the sign bit, then a 1001, the very first 1 would be a negative number, and the 001 would be the magnitude, which is a 1, will be a negative 1. If we're not using the sign bit, then a 1001, we have an 8 and a 1. When I add them together, I get a 9 base 10. It would be a 9. So you got to know if you're using the sign bit or not. Now, I know I went through that kind of quick, but that's okay. We'll go back and we'll revisit this, and I'll show you what I'm saying here with this sign bit stuff. Okay, let's do the ones complement. It's super easy. The ones complement is super easy. To get the ones complement of a binary number, all you got to do is invert the bits. Just flip them. So on this example, you see we got a 1, 1, 1, 0, 1. To get the ones complement, I change every 1 to a 0 and every 0 to a 1. So over here, all I did was flip the bits. Guys, I know I'm going over a little bit. If you got to take off, go ahead and just watch the end of the video when I post it to YouTube. You can watch it and pick up the lecture. But I'm almost done. I got 2 more slides. So ones complement, easy to do. All you do is flip the bits. Twos complement is still easy to do. It's a little more to think about, not as easy as the ones complement, but still pretty easy. Here's what you do. What you do, did somebody put that circle on there, or did I do it? I don't know how that happened. Anyway, what you do for twos complement, if you go on YouTube, they're going to tell you if you want to take the twos complement of a binary number, take the ones complement of it and then add 1 to it. You can do that if you want. But a much easier way is this. What you do is up to and including the first 1, you leave the bits alone. Let me say that a second time. Up to and including the first 1, you leave the bits as they are. After that, you take the ones complement. So this example, up to and including the first 1 is this group right here. Up to and including the first 1, I leave those alone. I just write those as they are. And then after that, all these bits after that, all of these, you take the ones complement, so you flip them. So now this whole thing right here, when I put those together, represents the twos complement. Now, if you guys don't understand that, when we log on Wednesday, please ask me to do an example of either the ones complement or the twos complement or both. I'll do examples if you need me to. So that really is it. This says we're going to focus on the twos complement, as I said, but that's all for binary number to binary number systems. So what I want to do next time is we're going to talk about how to do simple arithmetic with binary numbers. Anybody have any questions for me before we sign off?
I have a quick question. Oh, sorry, my bad.
Oh.
Go ahead, Jacob.
Hold on, Jay. All right, go ahead. I'm trying to turn the volume up. Go ahead. Let me see if I can
Can
hear
you go to the last slide?
Yeah. The
Thanks.
twos complement, this one?
Yep. Thank you.
And then my question was, if you're using the sign bit, do you lose that bit that has the value of 8? Because you're taking that bit that's out in front?
Yep. That becomes a sign now. And
So you
the
just
one-
start with the
one-
4.
Yeah, that becomes, you lose the value. That's no longer a weight. That's the sign bit.
Gotcha.
Anybody else have questions?
Yeah, I've got questions about the quiz from last night.
Okay. Wait a minute. Let me, can I get off the, anybody still need to see the PowerPoints? Can I get off these? Okay, I want to go to the camera so I could. Well, somebody sent me some questions. I didn't even know the questions. Let me get back to the camera. Okay, go ahead. You have a question about the quiz?
Yeah, I'm trying to find I wrote everything down that I had questions about. I'm trying to find it right now.
Okay, take your time.
Real quick before you ask about the quiz, I was under the impression that the quiz would be during class today, so I was not able to take it because it was locked out at 9. I know that's my fault, but is there any way that you could open that up again so that I can take it real quick?
That's a good question. Who am I talking to?
Blake Opria.
Blake. This is kind of weird, but I can't. Where I am now, I can't log on to Canvas.
Okay.
Tell you what. Why don't you text? Oh, I'm looking at the. Why don't you give me a text later this evening, and when I'm at home or if I'm in my office, I can unlock. It's kind of weird. I just can't. That the way they have the login, I don't have a cell phone, so I don't have a way to log in here. It won't let me log in unless I'm by my landline or some other method. So if you give me a text later when you're not doing anything, maybe in the evening, when I can log on, I can do that. I understand what you're saying because that's kind of the way it worked out. It was going to be Friday, but I told everybody I was going to give them the whole weekend to do it. So yeah, I'll do that for you. But just give me a text sometime after 5 and see where I am, and then we'll. Well, you know what? The problem is though the answers are already posted. I don't know if I can do that now. I had it set up. I just thought about it. I had it set it up to where at 10 o'clock the answers show.
Okay.
So like 5 minutes ago, you may just have to drop that one. I mean, I'm going to drop. I don't know if I said 2 quizzes. I'm going to drop the 3 lowest quizzes, so it's not going to hurt your grade.
Okay. Well,
You still want to see what the questions are because that might help you with the exam. But yeah, sorry, I was going to do that for you, but I had it set up to show the answers right after class today, and I don't know if that'll be fair or not. Let's just drop it. We'll just drop it. It won't hurt your grade.
okay.
Sorry about that. Did someone else have any questions on the quiz?
Yeah, I found my, I got my paper in front of me now. So.
Is that Hunter?
Yep.
Okay. What's your question, Hunter?
There are a couple questions that I thought I got correct that were marked as wrong, and I just wanted to go over those and
All right, let's do it.
ask whether or not, figure out what your policy on that was.
Okay, which one?
The first one was 6. It said 5 volts can be used to represent a binary value of blank. I put in 1, comma, or high because I didn't know which one would. The 1 was obviously correct, but I added more than the 1, and it was just looking for a numeric value, so it counted as 1.
Oh, yeah. So you know what I'll have to do, Hunter? I'll have to go in and grade yours by hand because I see what you're saying. You're correct, but I think the way when you set those questions up, you have to define the field as a number or a character, and you put in something else, so it probably didn't recognize that.
Right.
So what I'll do is, what I would do, I will wait because I'm done here. I'll be done this evening. I'll wait till like after 5. I'm more likely to be at home on my computer around that time. And you send me a text, I'll go in and I'll grade yours by hand. I'll give you credit for that one. That's number 6.
Yeah.
Hold on, let me write this down. Give me 1 second. I'll just write it in here. Okay, so number 6. What was your other question?
I've got 2 more.
Okay, that's fine.
The other one was 8, number 8.
All right, do you know the question?
Yeah, I've got it written down and I've got it abbreviated, but the general idea is the frequency is 4,000 hertz. What's the period in seconds?
Okay, we're looking for this.
I have the same question on that one too.
Okay. Yeah, so you should have had, so we said, I think it said F was 4 kilohertz. So the period will be 1 over 4 kilohertz, which is 0.25.
Should be 10 to the minus 4. 10 to the minus 4.
10 to the minus 4. I'm not
Yeah,
following. Where'd you-
I put in my answer as 0.00025, and it automatically rounded it up to
Yeah,
0.003.
That was
Affected my answer.
It rounded to 0.3.
yeah, that was my question on number 8.
Ooh. Okay, that's not. Oh, that's bad. Okay, so number 8. So you're saying the system rounded to 0.3?
Yep.
Correct.
Wow, because the weird thing is when I made the quiz, I actually took the quiz. It took me I went through it in like 3.5 minutes, and I put in the exact values of 0.000, and it gave me the right answer. I don't know why for you guys it would round, but I'll check it out. So it's number 8. That means I gotta grade everybody's by hand. Then if that happened, I have to go through and grade all those by hand. What about the other question? Is it number?
It's number 10.
What did that one say?
It was I think it started. I think in 9 and 10 were worked in tandem. but it's saying you're going from a serial to a parallel.
Yeah.
But serial to a parallel register, I guess, but it didn't mention what type it was. So I didn't know how you wanted us to do that problem, or either that or I'm missing something because
So the way that I think, and I don't remember what the numbers were, but let's say on number 9, I think they were together. So on number 9, you have to find the bit time. You have to find the bit time, which was just the period. I don't know what the frequency was, but you found that period. So let's say it was, I don't know what it was. Let's say it was 10 microseconds. I think number 9, do you have question 9 written down?
I don't. I can look it up really quick. I have it right.
I think it asked the question, I think it asked if you have 8 bits, how long will it take
Yeah,
to move the bit?
I've got it right here. I can read it to you if you want.
Go ahead and read it.
It says if the clock speed of a digital circuit is 2 kilohertz, how long will it take to transfer 64 bits serially?
Okay. So there, if it's 2 kilohertz, so frequency is 2 kilohertz. What you said?
Yep.
That's what you said? So then we find the period. The period would be 1 over 2 kilohertz, which is 0.5 milliseconds. So that would be the bit time. And then if I'm transferring 64 bits in serial fashion, that means it's going to take 0.5 milliseconds times 64. Because the bit time defines 1 bit, so it takes 64 basically pulses for each bit. So it'll be the 64 times the 0.5, half of that. Or 6.4. In parallels like this, I got all 64 bits, and of course, I'm not gonna draw 64 bits. I got all 64 bits, whatever they are. The clock clicks 1 time, basically, what was it? 0.5 milliseconds. And in parallel, all those bits are transferred on 1 clock pulse. Do you have, let me see if I still have it. Hold on a second. Let me see if I still have the diagram where I don't know if you're following me, because let me see if I still have my, I don't think there was an example of data transfers when I'm looking for it. I may have gotten rid of it. I was going to refer to that diagram. But do you follow what I'm saying or not?
Yeah, I get what you're saying now.
Was it confused? I mean,
but I didn't realize that I was thinking of like an 8-bit or a 16-bit register, and I forgot that they could get up to be 64 bits. I forgot they could get to be that big. So instead of dividing that time by 64, I divided it by 8 because I was using an 8-bit register.
Oh, okay.
I didn't know what to use, but now that I get what you mean now.
Okay. Well, tell you what, I'll go in and I have to grade number. So how'd you do on the quiz? Like, what kind of grade did you get?
I got a 70.
But you got 6 and 8 right, correct? Is that right?
I got them correct. I mean, I got them correct. Yeah, that's why I asked about them. Yeah, because I knew I got them correct.
I think you got those correct. So you'll end up with a 90.
Right.
Yeah. So yeah. I mean, I don't know about the data transfer question, but I'll go in and fix 6 and 8, and you'll end up with an A on the quiz. And I'll have to go in and see why it rounded the numbers for those, and probably grade everybody's by hand. That's what I'll have to do. But I'll take care of it.
All right. Thank you.
Thank you for pointing that out. I didn't realize it did that.
Yeah, for
I was
sure.
also wondering, is there like a separate formula for parallel that you would have to calculate it by?
No, it's just 1 bit time for parallel.
So it's just a bit time. It's not that times the amount of like having 64 bits times the 0.5 microseconds?
If they're in serial, if they're in series, it is serial.
Okay, so that's just for serial, and then the bit time specifically is for parallel, since it all
Yeah.
goes at once. Okay.
Yeah, does it make sense? You see why or not? Do you see why?
Yeah, I see why now.
Okay, all right. Yeah,
All right, thank you.
okay, you're welcome. And I'll go in and I'll look at 6 and 8 and I'll fix those guys. Thank you for pointing it out. Jacob, Benjamin, Christian, any of you guys have questions?
I guess the only one I have is about question 8 as well. I think I did that one right, but no, question 9.
I'll fix that. Yeah, I'll fix that. I'll go in and just do it by hand because I don't know what the system did. But yeah, I'll fix that. You'll get credit for it.
Sweet. Thank you so much.
Okay, guys, have a great rest of the day. Please stay safe. I'll see you guys on Wednesday.